In this video, I will explain you how to sketch a rational function, such as the one you can see over here. The sketching principle can also be applied to other functions, such as e to the minus x sinus x, or, for example, sinus x over x, or, for example, a quadratic function, or any function that you can think of. So, in order to sketch a function or to obtain its graph, we need to perform the following 4 steps. So first of all, we need to find the function's zeros. So what are the zeros? The zeros are points at which the function crosses the x-axis. That is when y is equal to 0. The second step is to find the vertical asymptotes. So what are the function asymptotes? Well, for certain values of the parameter x, let's say, for example, if x is equal to 5, the function might go to plus infinity, minus infinity. So these are the vertical asymptotes. They are vertical lines at which the function takes plus minus infinity. Similarly, horizontal asymptotes are lines, in this case horizontal lines, that function approaches when it goes to plus, when x goes to plus or minus infinity. And finally, we need to investigate the function monotonicity. So what is the function monotonicity? Well, we want to investigate for which values of x function is increasing and for which values of x the function is decreasing. So by performing these 4 basic steps, we can sketch the function graph. Okay, so let's start with the first step, zeros. So the question is, when does a rational function have zeros? Well, the zeros are determined for the values of x at which the numerator is equal to 0. So we want to find the points for which the numerator is equal to 0. This numerator obviously can be written as x minus 1 squared. So the only 0 that we can find here is 1. Actually, since this is a quadratic function, it has 2 zeros, but both of the zeros are equal to each other and they are equal to 1. So we know that the function will be equal to 0 at 1. The next step is to investigate the vertical asymptotes. So, what are the function vertical asymptotes? Well, we want to find the values of x for which the function will be equal plus or minus infinity. Obviously, function becomes plus or minus infinity when the denominator is equal to 0. Or we want to find values of x for which the denominator is equal to 0. Obviously, when x is equal to 5, the denominator will be 0. Now, if x is equal 4.9999, many nines, the denominator will be negative. will be very small and it will be a negative value. Consequently, the function will be equal to minus infinity for x that's very close to minus 5, but from the left side. You can verify this by using a simple calculator. For example, if you substitute x, let's say 4.999, you will get 4.99999 minus 5, and in the numerator you will obtain a finite value. You will obtain something finite. So this will be finite equal to finite over something very small, negative small, and this will be minus infinity. So we know two things. We learned that at 1, the function will be equal to 0, and we know at 5, when x tends to 5 from the left side, we know that the function will go to minus infinity. Similarly, when x is equal to 5.000001, the function will become something finite over 5.000001 minus 5. This will be equal to something that's finite over something that's positive and very small number, so this will be plus infinity. So we know that when x approaches 5 from the right side, the value of the function will go to plus infinity. So when x goes to 5 from the right side, the function will tend to plus infinity. The next step is to investigate horizontal asymptotes. So we want to see what is the limit value when x goes to plus minus infinity of the function y. So let's first investigate what happens when x tends to plus infinity. Well, if x tends to plus infinity, we can see that this function approaches infinity. Why is that? Well, imagine that x is equal to million, so it's 10 to the power 6. The numerator will take the following form, and the denominator will be equal to this. So what happens? The denominator will approximately be equal to 10 to the power 6. And the numerator will approximately be equal to 10 to the power 6 squared. Why? Because 10 to the power 6 squared, this term, is much larger than two other terms. So the function will be equal to 10 to the power 6. Will approximately be equal 10 to the power 6. We neglect here the terms that are of lower order. So if you substitute here 10 to the power 20, you will see that the function becomes equal 10 to the power 20. That is, we can see that when x tends to infinity, the function tends to infinity. Why is that? Because the maximum order of this term, the oldest term in the numerator, is much larger, is actually not much larger, it's larger than the maximum order of x, which is in this case, in the denominator, which is in this case equal to 1. So we know when x tends to infinity, the function will go to infinity. Similarly, you can show that when x goes to minus infinity, the function will go to minus infinity. Why is that? Because the denominator will be negative and the numerator will be positive, and similarly you will have 10 to the power 6 squared over minus 10 to the power 6, and this will be minus infinity. So we know that the function, when x tends to infinity, negative infinity will go to negative infinity. Okay, so the final step is to investigate the function's monotonicity. So how can we do that? Well, we just compute the first derivative of a function, and we want to investigate the sign of the first derivative. So we want to see the sign of the first derivative. So if the first derivative is positive, the function is increasing. If the first derivative is negative, the function is decreasing. If the first derivative is equal to 0, the function has a maximum or minimum at the corresponding values of x. So let us compute the first derivative. So this is a rational function that can be represented as g of x over some f of x. And the formula for computing the first derivative of a rational function is the following. So we square the denominator and we take the first derivative of g of x multiplied by f of x, then we subtract g of x from the first derivative of f of x. So let us substitute the values. In the denominator we have x minus 5 squared. In the numerator, the first derivative of g of x is 2x minus 2 times x minus 5 minus, what is g of x? Let us write g of x in the compressed form. And what is the derivative of x minus 5? It's simply 1. So let us write this in a condensed form. So in condensed form we have x minus 5 squared. Now notice that this term can be written as 2x minus 1, and we can observe that we have x minus 1 here and x minus over here. So we can write this expression as x minus 1 multiplying x minus 5 2 times actually x minus 5, right? Since we have another 2 minus what? Minus x minus 1 multiplying 1. So what do we have at the end? Our first derivative becomes x minus 5 squared, and we have x minus 1 multiplying, let's see, here we have 10x, sorry, it's not 10x, it's 2x minus 10 minus x plus 1. So this becomes x minus 9. Okay. Now, the next goal is to investigate the sign of this function. Now, we see that first derivative is again a rational function. In the denominator, we have a positive value. So no matter what x is, whatever you choose for x, the denominator will always be positive. So the sign of y prime of x is determined by the sign of the numerator. So let us investigate the sign of the numerator. Now, the numerator is a product of two functions. So let's first investigate the sign of x minus 1. So this function change the sign at 1. So when x is smaller than 1, x minus 1 is negative. And when x is larger than 1, x minus 1 is positive. Now, let us investigate the sign of x minus 9. Obviously, this function changed the sign at 9. When x is smaller than 9, this function is negative. When x is larger than 9, this function is positive. So the sign of y prime, or the sign of x minus 1, x minus 9, will be determined by the product of these two functions. So here's how we can quickly figure out the sign. So what happens here? Negative function times a negative function gives something that's positive. Negative function times something that's positive gives a negative function. Something that's positive times something that's positive gives a positive value. So this is the sign of y prime. So y prime will be positive from 0 to 1. It will be negative from 1 to 9, and it will be positive from 9 to infinity. And this implies that the function y increases from minus infinity until 1, right? Increases. Then it has a maximum at 1, since the first derivative is equal to 0 at 1. So here we have a maximum. And then since y prime is negative from 1 to 9, this function will decrease from 1 to 9. At 9, the function will have the minimum value. So at 9 it will have the minimum value. And from 9 until infinity, since y prime is positive, the function will increase. Now, this is in accordance with the asymptotic values and zeros that we can see over here. So we can conclude that as x increases, the function increases, and it reaches its maximum at 1. Then from 1, the function decreases until negative infinity, which is never achieved, but at 5 it goes to negative infinity. Then function goes up, and from 5 plus it is plus infinity, it decreases. We learned at 9 that it reaches its minimum value, and then after 9 the function, you can see over here, the function increases. So this is the sketch of our function. This is how the function looks like.